Welcome back to NE 630 reactor physics. So today we will start a new chapter about reactor kinetics. But before we start the new chapter, let me give you the exam results. So there is, I think, nearly 35 students who took the exam. Not took the exam. 35 students total. I think there is something like maybe 20-something here and 10 or 11 online, so 31, 32 students who took the exam. The mean for the exam is 83. The standard deviation for the exam is almost 10, 9.64, and the median for the exam is 85. This is where the majority of the students got their grade. The minimum for the exam is 51, and the maximum for the exam, there is a student who got 97. So this is the maximum. If I will talk about, this is everybody. This is from online as well as the on-campus. The online, I think they did better than the on-campus. I do not know why. They got, the majority of them, they got the exam in the 80s, upper 80s. Maybe the minimum was something like 82, 83. The maximum, nobody got 90s in the online, although the 90s are here, lots of 90s in the on-campus. But overall, I think the online cohort, I think they did also good. I did not take many points from the exam. If you look at your papers, you will notice that sometimes I give you a grade, then I take it off, then I increase it a little bit, then I take it off and I increase it again. So the person who got 51, for example, he should get something like 20. But I started giving him points here and there so that he will not fail the course. So again, my intention not to fail anybody in the class. My intention is to help you guys understand the material, which is more important than just failing the class. I do not want to jeopardize your learning here. Again, in order to be also justice with everybody, I tried to give not equal points for the person who gave me an incredible answer, for example, versus somebody who gave just oh, yes or no, or increase, decrease without giving anything. Although I was extremely humble to give, even for when somebody say decrease and it increase, and I give something like does not make any sense, I do not take it a 5. Each one of those points, for example, for question number 3, worth 5 points. So you will notice that I write to you, for example, for the resonance escape probability P, it increases, and I will tell you why it increases. Some of you wrote it decrease, and he gave something that does not make sense. So although he wrote the wrong answer and he gave the wrong answer, I do not took the 5 point off. I just gave 2 out of 5. I try to be so generous with everybody so that nobody again will fail the class and everybody will be happy about the grade. If you have any concern about whether you deserve the grade or not, you can come after the class and see me. If you have any comments, your grade, you feel like, okay, you are oppressed inside this grade or whatever, just come to me and we'll discuss it individually. So for the first question, which is just define the following, and I wrote in between brackets, use formulas whenever applicable, for example. I noticed that the class divided to 2 parts. One who just wrote some wording, the first part. The second part who wrote just formulas, and there's no definition. So define means you have to define in verbal words and then use formulas to assure that what you are saying is true. So for example, in the binding energy, I got lots of flavor in defining the binding energy. Students who talk about binding energy in chemical reactions, for example, so or atomic binding energy. We are not talking atomic course here, and I am telling you to define the binding energy, which is the nuclear binding energy. It is obvious that this is a nuclear reactor course, and this is the nuclear binding energy, not the atomic binding energy. I was not expected that you will write something about the atomic binding energy. Again, for the K effective, everybody except 2 or 3 students who wrote, yes, you wrote the 6 factor formula, and you said this is the K effective, then you said it is the number of neutrons generated in nth generation over the number of neutrons generated in the nth minus 1 generation. This is the definition for K effective as well as the K infinity. If you just say that the K effective is number of neutrons generated in the nth generation over the previous generation, this is the definition for both, for K effective and K infinity. But you have to define the K effective, and K effective is for finite system, finite reactors. K infinity is for an infinite reactors. So this is the difference between K effective and K infinity, and K infinity does not have any non-leakage probabilities. So it is only the finite system that has the non-leakage probability. You have to be clear about this. So you will see that sometimes I took 1, sometimes I took from the definition 2 if your definition is completely off the track, and sometimes if I feel like I calculate the total number of buoyants and I notice that you will not get enough grade in the exam. Although I took -2, I return it back and I cross it and I say -1, so that I will be more generous again with you guys, so that you will get good grades in the exam. Again, I'm not telling you this to say, oh, I'm giving you points for free. No, I'm telling you this you still have the chance to do very good in the course. All what I care about is, did you understand the material or not? And the exam was just something like a realization of who understand the material and who just copied from the book the definitions and stuff like this, because he does not know what's going on. So for the prompt and delayed neutrons, the majority of the students define the prompt and delayed is one is born directly from the fission, the other is born lately from the fission also, which is in a sense true and in a sense not true. It's not directly born from the fission. The prompt neutrons are when you have the fission, you have the fission products, then the fission products will have beta decay, then you will reach to certain radioisotope, they call it delayed neutron precursors, because those isotopes will decay by emitting neutrons. So then delayed neutrons, they are not directly coming from the fission process, they coming from the fission products decay, and then they will emit the neutrons. Again, if you wrote those two definitions, usually I do not take anything. But if you did not write the distinction between both, usually I take 1 point or 2 points. Not every student define what's the role played by delayed neutron and prompt neutrons. And again, I was expecting that you will tell me that neutrons reactor without delayed neutrons will be hard to control. And there is only 1 or 2 students who just mentioned this. Characteristic time 10 to the power of -14 for prompt neutrons from fission. Delayed neutrons is a fraction of a second up to 60 seconds. Again, not every student wrote this, which is very important. If you try to write a report to your manager in a nuclear reactor and he asked you for a presentation that you will present for the upper level managers or for somebody outside, if you do not know what are you talking about, it will be very bad in your side. It will be extremely bad. People will, I used to work in industry for 4 years. They will throw papers in your face if you do not know how to articulate what are you talking about. It's very, very bad. You have to know what are you talking about, then you define it. Diffusion length and migration length. All the students except 1 or 2, they just define L equal to square root of D over sigma absorption, M equal to the square root of L square plus tau. That's it. Okay, two equations. I am an illiterate guy. I want to know what does it mean. You never even say what's D, what's sigma, nothing. Just say what this. This is not a definition, guys. So again, and I told you that the definition, the majority of the students wrote that the diffusion length is the distance between the neutron was being born to the neutron being absorbed. This is not true. It is the average. It is the average process, and we showed that R square average 1/6 R square average is L square, and this is for thermal. and 1.16 r square average for fast. Let's say this is tau, and m is just L square plus tau, and this is m square, for example. And again, I told you guys that this has a definition, this has a definition. For this one, the neutron is born here, it makes frequent collision, for example, here, 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 and then finally it gets absorbed here. But this point, you are generated as thermal. So you slow down from the slowing down region until you reach the thermal. Once you reach the thermal, you will start diffusing inside the medium until you finally get absorbed here. So this is the mean, the crew flight distance. And this is R. So if you take R and you average it all the neutrons, you will get the average of the square of R thermal, which is this, and you divide it by 6. This gives you the diffusion area. The square root of this will give you the diffusion length. You have to tell me physically what does it mean. Okay, so again, I took only 1 point or 2, and that's it. Spatial self-shielding, and this was very interesting one, because we did not at this time discuss anything about energy self-shielding. And the majority of the students, they define the energy self-shielding. So they just got what's in the book and they split it in the paper. Although I did not define the energy self-shielding. So you knew that the equation for the flux goes like what? 1 over sigma absorption as a function of E plus sigma scattering as a function of E multiplied by E, and it is modified by exponential term here. So whenever you will have the absorption cross-section increases, and this is at the resonance, you will notice that absorption increases, so the flux will go down, and this is the flux here. So we defined this way after we took the exam.
But you defined the other in one of the lectures.
Yes, I'm not saying anything. I said we defined this after we took the exam. But I saw that everybody defined the self-shielding as this. It is exactly true. This is the self-shielding, but this is called energy self-shielding. But because we did not take this until later after the exam, I expect that everybody will define the spatial self-shielding. And this is the spatial self-shielding, that the few outermost layers of the fuel, they will absorb, because they have very high absorption, they will absorb the neutrons, and this will affect the chance that the neutron will penetrate into the core of the fuel. And this is why you will have a dip in the flux inside the fuel. So you have to define it like this. This is the spatial self-shielding. And this is the energy. This is the energy self-shielding. And again, there is students who define both, and I give credit, I give full credit. Whoever wrote this, I give him full credit. Whoever wrote this, I give him full credit. If you just spit this blot without defining anything, I took 1 or 2 points. So the second question was a gift. It's just a direct substitution, 1 line. Everybody got the question right except 2 or 3 students. 2 students, I think they make everything, they show the substitution. When they do the numerical calculation, they got it wrong. They got it 100 or 80 MeV or 77 MeV or something like this. I just took 2 points because this question is 20. So it's just I'm giving you 20 points for nothing. It's just a direct substitution. So I just took 2 or 3 points. There is only 1 student who wrote completely wrong formula. And it was the formula for binding energy. And I was surprised because I give you already the formula. Why you put your own formula? I told you the formula in the exam for the separation energy is given by this and that, and I give you all the parameters that you want to use for calculation. Just it is a direct substitution. So you will notice that all of you got 20s, but maybe 2 or 3 students who did miss the calculation. For example, I took 2 points or 3 points off. The most problematic question was number 3. And this one also has a 20 points. So it asks you about epsilon. So epsilon is defined as the fast fission plus thermal fission divided by thermal fission. So you increase the volume of the moderator divided by the volume of the fuel. What does it mean? You have more moderation. So Vm over EF means more moderation. What does it mean? More moderation, so you will have more thermal neutrons. More thermal neutrons mean if this is the cross section, for example, here you are populating more thermal neutrons because you have more moderation. So you will have more thermal fission and you will have slightly less fast fission because the neutron energy will get a little bit shifted toward the lower energy part. So you will have a slight decrease because the fast fission will go a little bit lower, okay? And the thermal fission will be a little bit higher. So you'll have a slight decrease, very slight decrease. Students who give me no change, I give them full credit. So even if you say no change, I give you full credit. But if you just say no change and there is no why, I took 2 points off. If you don't mention anything like just say increase, decrease, increase, decrease, of course I have to take points off because I said why. After each one I say why. If you do not say why, of course in order to be justice, there is students who did very well and they wrote why for everyone and very good explanation. If you do not say anything, I will take points. So this is the thermal fission. So what about P, the resonance escape probability? P is just given by the exponential of what? Minus, what's the VF over VM divided by XZ sigma scattering, I think. Yes? And this ratio will do what? Will decrease. If VM over VF will increase, so VF over VM, the inverse, will do what? Decrease. If you have an exponential function, e to the power of x versus x minus x, and it is like this. If you decrease the value of x, you are going toward higher value of what? E to the power of x. Yes? Yes? And this is why you have it like this. So if you increase the moderator ratio compared to the volume, mathematically this is why, but usually if you increase the moderation, you will have better chance that in one collision you will encounter more of a moderator compared to more or less of a fuel. So you will have more of chance that you will be far away from the fuel and you will be more in the moderator until you lose all the energy. Then you will get into the fuel to induce the fission again. Did you understand? So let's assume that this was the case, fuel and then moderator, then you increase the volume of the fuel, moderator compared to fuel, so you reduce the fuel like this. So if the neutron gets out from here and gets to the moderator, it will start doing what? Collision until it what? Encounter again the fuel again. So here you spend 1, 2, 3, 4, 5 collisions. Here you will have something like this until you return back to the fuel. So here you have a better chance that once you return back to the fuel, you will be more thermal, but here, of course not. So there is a better chance that you will lose the resonance energy while you are in the moderator compared to the situation. Did you understand it why? I think, guys, I do not think that we are writing magic here on the blackboard. It's very, very simple. Just if you concentrate, and I knew in the exam, sometimes you have, what, I don't know, it's, I call it exam symptoms. that you will feel like, okay, I want to go restroom. I have lots of my friends when I was in the undergrad like this. But if you are solid and sit down and there's no problem, if you want to make it in your place, and that's it, you will have something like this. It's very tough. I know the exam is sometimes you have allergy against exams. But if you think about it, it's nothing. Okay, guys. What about F? So F is just what? Sigma absorption in the fuel divided by sigma absorption in the fuel plus V moderator over V fuel multiplied by what? Sigma absorption in the moderator. Again, if the absorption does not change because you do not, if you change the amount of moderator, you do not change the sigma absorption. Why? Because sigma small is a constant and number density is a constant. It's a specific property. It does not change with how large or how small. Sigma absorption fuel is the same. If Vm over Vf increases, so the denominator will increase, the numerator, the total fraction will do what? Will decrease. And that's it. Yes? Yes? Okay, guys? So this is the thermal utilization. How much you absorb inside the fuel compared to how much totally you absorb. If you increase the amount of volume of the moderator, you have more absorption in the moderator compared to the fuel, and your utilization of the neutrons is lower physically. Okay, guys? Then lastly is eta, and eta is what? Let me write eta in a... Eta is what? It's eta is just nu multiplied by sigma absorption, sigma F for the fuel divided by sigma absorption in the fuel. Everybody saw this and he said it does not change. But technically speaking, there is a minor change. Why? Because eta, this is for just homogeneous reactor. But we are talking about heterogeneous reactor like this. So sigma fission and sigma absorption just are the average, and those are average over what? So sigma fission as a function of energy E multiplied by the flux in the what? In the fuel as a function of energy E dE, but also you have to integrate over the volume. Yes? So and then phi in the fuel as a function of energy E dE. And sigma absorption, you remove sigma fission and put sigma absorption. So the flux in the fuel and the flux in the moderator, phi in the fuel, phi average in the fuel to phi average in the moderator to the phi average in the fuel. This is given by this parameter, which is the thermal disadvantage factor, which is a parameter that depends on what? Is a function of Vm over Vf. So if Vm over Vf will change, the thermal disadvantage factor will change, and the calculation will change. But this ratio will be very minimal. The change is very, very minimal. So if you say it will not change, I give you full credit. Okay, guys? So did you understand now where are your mistakes, or where were your mistakes? Okay, now the last one is the problem. So the problem is 35 points. I give 20 points for part A and 15 points for part B. So part A, your solution this is, you will solve the nabla square phi minus 1 over L square phi equal to 0. And you said that phi of R, you will reach to the definition that it's C1 e to the power of R over L divided by R plus C2 e to the power of minus R over L divided over L. Of course, you will do, in order to solve this, you will get psi equal to what? Phi R, I think. Okay, then you will substitute, then you will reach to this solution, then you will or you will have the final solution like this. All of you said, okay, we will assume that our solution is C1 sine sinh R capital minus R divided by L plus C2 sinh. Everybody except two students or so, they said, okay, we will assume that our solution is like this. You assumed your solution is like this. You can assume, and it will be right if you said it is C1 sinh R, C2 cosh R. Cosh R. But why you substitute R prime minus R over L? This form here will come from the fact that you will substitute for the boundary condition. And the boundary condition is the flux at R small equal to R extrapolated equal to 0, and then the limit when R goes to 0 for 4 by R squared multiplied by J of R is equal to the source term. Those are the two conditions. So if you have this as a function of R, then this as a function of R, then you will say phi at R equal to Z, R equal to R, so this will be sinh of R capital. But everybody said, of course, when you do this equal to 0, you will then get C1 as a function of C2 and so on. But I noticed that everybody just assume something like this. Then when you substitute, you fall into the problem that you will say, okay, at R equal to R tilde. R equal to R tilde minus R tilde over L is 0. R tilde minus R tilde is 0. So cosh of 0, sinh of 0. Then I heard, oh, we will cancel C2. Some of the groups say we will cancel C1, and it is very easy to show. Split the formula in the book, put in the exam, and it can be shown that this is phi equal to the formula in the book. You fall into the problem because this is not the way you do it. This is not the way we did it. The way we did it, we said either this, or you will propose that the solution will be e to the power of R over L over R, e to the power of minus R over L over R, or you said that my solution is phi of R is equal to C1 sinh of R plus C2 cosh of R. Yes, guys? So why you put here R tilde minus R over L? It does not give you anything, and all of you fall into the mistake that when you try to apply the boundary condition, you get wrong answers. And you come here and then you said, okay, phi at R equal to R tilde is equal to 0, and then 0 equal to C1 multiplied by sinh of R tilde plus C2 cosh of R tilde. Then you have another formula that limit for R multiplied by 4 by R squared multiplied by J of R when R equal to 0 is equal to SP. Then when you have this formula, you will differentiate this one, and you will have C1 cosh of R plus minus C2 sinh of R, and this will be what? Multiplied by negative D. This will be J of R. Then you will take J of R multiplied by 4 by R squared and substitute when R equal to 0 equate to C2. So you have two formulas in C1 and C2. You will solve these two formulas and you will get C1 and C2. That's it. But everybody make the mistake that, okay, we will assume that this is phi tilde, R tilde minus R over L. And this is not right. Did you know where is your mistake? Did you learn from your mistake? Okay, so this will lead to the flux. This will lead to the flux of R will be given by the following formula. It's SP multiplied by sinh of R tilde minus R divided by L divided by sinh of R tilde over L multiplied by 4 pi dr. So this is the flux. Now, if you just do something and then write this, I give you, and I did not write completely part B, I think the minimum I gave was 15 or 16. If you do not write anything, I give you 5. I think I give somebody 5 who does not write anything. Just as the Halloween gift. Okay, guys? So, for part B, I asked you for the leakage. Okay, one of the mistakes. It says a finite sphere with a source inside at SB at 0, R equal to 0. I noticed that there is a couple of students who said that the flux will be equal to 0 at infinity. This is not an infinite system. This is a finite sphere. And we have some neutron source inside. So if this is a finite sphere, we learn it from all the lectures. If you have a finite slab and you have a source here in the center that emit neutrons, we knew that the flux will go what? Will go to 0 at what? A tilde, which is extrapolated distance. If we have a cylinder, it will be at R extrapolated and H extrapolated. If we have a sphere, it will be at R extrapolated, the flux will go to 0. So I do not know why some of the students wrote that the flux will go to infinity. The flux will go to 0 at infinity. We are not talking about an infinite system. Again, one of the problems. The second part, I asked you for the leakage from the system. So the leakage from the system, you can get it by two things. What's the leakage? What's the definition of current? This is a sphere. There is no neutron coming from outside the sphere to inside the sphere. The only way is the neutron will get out. So J is a vector that represents how many neutrons per centimeter square per second that gets out from the sphere. So if you want a ratio, you have to get the total number of neutrons, which will be 4 by R square, which is the area of the sphere, but this is R tilde because this is the radius, major radius, R tilde, multiplied by the current at R tilde. Yes? So this will give me what? This is number per centimeter square multiplied by the area of the sphere, which is 4 by R square. So this is the total number of neutrons leaking from the sphere. If I divide it by the original number that's generated inside the sphere, which is SB per second, this is number per second, this is number per second, this will give me unitless quantity, which is known as the leakage fraction. Leakage fraction. You can also obtain the same formula if you will say that what leaks out is what's being absorbed here. Yes? So it will be 1 minus the fraction of what's absorbed here. So, and this is also equal to 1 minus the absorption what? Absorption what? Fraction. And what's the absorption fraction? This is equal to 1 minus, what's the absorption fraction? You will divide the total absorption inside the whole sphere divided by what? By SB again. So what's the absorption? Sigma absorption, it's a constant, multiplied by flux of R, it's a constant, multiplied by the unit area, unit volume, sorry. What's the unit volume? If you take a unit volume like this, so what's the unit volume of a spherical shell? It's R4 by R square multiplied by what? dr. And this is what? The unit volume. So whatever absorbed inside this unit volume. Okay, guys? And then you will integrate this unit volume from 0 to R capital. So from 0 to R tilde. Okay, guys? So you have the flux here as a function of R, and you have 4 by R squared dr, and SB is a constant. If you do this or you do this, you will reach to the conclusion Same conclusion. If you do this or if you do that, you will reach to here. You will just, to get J of R equal to R, you will just negative d phi of R by dr at R equal to R tilde. So you will differentiate this function with respect to R. This is with respect to R is what? Is a constant. Oh, there is R downstairs. Up to here is a constant. So it will be sinh over R. Yes? It's very simple function. F of x over g of x. Yes? You will divide, you will have the differentiation of a quotient. Yes, guys? So, in this case, if you do this, you will obtain, finally, this is the ratio here. 4 by R square tilde J of R tilde divided by SP. This will give you R tilde over L divided by sinh of R tilde over L. So if R tilde over L is equal to 1, this will give you what? 1 over what? Sinh of 1. There is a couple of students who reach up to here. They did not do this except one student. So only one student who got 97, he got this right. So 1 over sinh of 1. And this will be 1 over sinh of 1. If you do the calculator, will give you 1.1752, and the inverse of this will give you 0.8509, which is 85% will leak out. Okay, guys, again, the majority of you who does not do anything good here, and I think sometimes I give 28 out of 35, sometimes I get 29. It depends on how many points you need so that I can improve your score. You will notice that there is students who I put first 28, then I notice that he gets something like 60 or 70. Then I cross it and then return it back and try to see a point or two for him so that he will be above 70 or above 80 or above whatever. So again, did you get the, yes?
How do we get the denominator R tilde over L?
Huh?
How do we get the denominator R over L? R tilde over L?
This one?
Yeah.
Here it is. For the flux. For the flux function, it's sinh of R prime minus L over L divided by this function. Then take J of R equal to R prime, R tilde, sorry.
Yes.
Differentiate it with respect to R. This is a constant. This part is a constant.
Yeah.
So it will be taken outside here without anything. Then when you do this, there is a factor here 4 by R square.
Yes.
Okay, let me do it for you. So this is phi of R is SB divided by 4 by D multiplied by sinh of R tilde over L multiplied by sinh of R tilde minus R over L divided by what? By R. So get this as is divided by 4 by D sinh of R tilde divided by L. Now I want to get D, J of R. J of R will be what? Minus D multiplied by D phi by the R for this one, yes? What's this? R square. So, so this will be R multiplied by the differentiation of this, which is what? Cosh R tilde minus R over L multiplied by whatever the differentiation here, which is what? Negative 1 over L. Okay? Because this is constant. And the differentiation of negative 1 over R over L, the differentiation with respect to R, it is negative 1 over L. Okay? Minus the second, which is this sinh of R tilde minus what? Minus R over L multiplied by the differentiation of the first is what? 1. Okay, guys? So this will give me, this is the formula for J of R small. Okay, guys? So when R small equal to R capital, this is what? 0. Cosh of 0 is what? Is 1. And sinh of 0 is what? Of 0. Okay? So this will give me 1 over here. And R over R square is give me what? R. Yes? But when you substitute with R equal to R tilde, this will give you what? R tilde, yes? And this is negative 1 multiplied by negative is positive, divided by what? Divided by L here. Yes? So D goes with D, and then you will have what? And it was here, okay. When you will get this formula, you have to multiply by what? 4 by R square tilde. So 4 by R square tilde divided by SP multiplied by this, which is SP divided by 4 by R tilde divided by sinh of R tilde over L, and you have a factor here, L here. So R 4 by goes with 4 by, R tilde goes square, SB goes SB. You will end up remaining with R tilde over L divided by sinh of R tilde over L. Okay, guys? Did you know how to get it? So yes.
How do you know R tilde over L is 1?
I give it to you.
Okay.
I told you here, if R tilde equal to L in the exam paper. So R tilde over L is equal to 1. Very easy, yes? Okay. Okay, guys, I hope that you're satisfied with your grade. And again, the main reason here for this exam is not to torture anybody, it's just to give you an idea where are you located in the course. Okay? I hope that everybody is happy and satisfied. And again, I hope that next lecture will start the new chapter. Have a wonderful time, and let me know if you need anything.